Okay, so if we're looking at the data set, let's start. Generally, I would suggest steady state. So if we're looking at the data set, first thing is the nature of the data is exponential. So what we don't see in it is, okay, there's a bit of variation on the top, but I classify that as noise. You know, so the stuff that's happening here after 6 seconds, those variations are pretty much noise. What we don't see in that data set is kind of an obvious overshoot, which would look something like that. Okay? Those things are characteristic of second order systems or higher order systems, if we have overshoot or oscillations in the data. So the absence of those things would suggest that it's first order, right? That we have a first order, that the data represents a first order system. And if it's first order, then we can model it as, well, at a minimum with 2 parameters, which would be my steady state gain, which I'm going to call KSS. I'm not too sure if that's the same as what you would have seen before, more or less. But anyhow, it's the same meaning, the steady state gain. And we have a second parameter, which is my time constant. I'd suggest the steady state gain is the easier of the two to estimate. What's the definition of the steady state gain? More or less even an intuitive definition of this one.
The average result. The change of the value at the start of the
okay, so yes, so more or less the simplest definitions we're looking at output over input. Okay, so in our case, our input is the blue signal, our output is the red signal. Without taking any measurements, more or less, what do you expect the gain to be?
Just over 1.
Just over 1. Okay, so if we were to just look at those two, my output is slightly larger than my input signal. It's not hugely larger than my input signal. It's not double my input signal. So if it was double my input signal, it would be going up to 10 volts. The output, the red signal, would be going up to 10 volts. So intuitively, if I look at that, I'm expecting my gain to be about 1. Okay, thereabouts. Slightly larger than 1, but more or less 1. Right? If I'm not getting something like 1, I'm doing something wrong. Okay, so that's the first thing. Now we'll come back and actually calculate the thing in a minute. But intuitively, that's what I'd be expecting. The other parameter is my time constant. Right? The time constant is measuring the speed of my response, so how fast my response changes or reacts. Right? So when I'm looking at my when I'm looking at my time constant, I'm looking at when does it start to change? When does it finish kind of changing? And technically my time constant is the time it takes to get to 63%, or just over half that transition. And again, like, it's really useful at the start, before we go making any calculations, to actually look at the data and make a guess at those things, so that when we go back and do the calculation, we go like, am I right, or am I obviously wrong? So if you were to look at that data, look at where the response, that's the red signal, the red dotted signal, begins to change, the time when it begins to change, the time when it finishes changing, and more or less 50% of that. What sort of time are we looking at? What sort of time scale are we looking at? Right? So I would be, so like the 2 points that I'm looking at in time are here, where it begins to change, and we're looking at up here where it sort of finishes changing. Okay, I'm assuming that after this it's noise. So I'm looking here, if I was to roughly guess that, that's like 2 seconds. Half that's going to be about 1 second. So our time constant is 63% of that, so it's going to be a little bit more but I'm expecting something like a second as a measurement for my time constant. Right? So, I think when we're, and I guess this is one of the common misunderstandings or mistakes to make when we're measuring our time constant is to take the absolute value of time. So I start at 0, I take my time constant here is about in around here, for example, and therefore I've got 5 seconds of a time constant. I don't, in any of your cases, in any of the data that you're going to collect, that's not the case because my input signal does not change at time 0. You know, there's a lag there, or there's a delay. So the first part of the data, your input signal is likely to be at 0, and then it jumps. I think most cases it's probably around 5 seconds that transition happens. So you're starting your measurement of your time constant from that 5 seconds. Right? Or actually it might be even longer than that. But as I said, that's one of the common mistakes that's made, or one of the common misunderstandings that's made when we're estimating our transfer functions, is to neglect to think about maybe when my input signal actually happens, and therefore we end up with a slightly incorrect measurement. So as I said, we're starting off with a transfer function. The assumption is that it's first order. My steady state gain, which is the KSS. I probably have this in the handout someplace, is technically it's the change in my output divided by the change in my input. So if I'm zoom up here, I'll go up there. If I'm looking at that data set, my input signal changes, the time when my input signal changes, as I said, is 5 seconds. So the amplitudes I'm going to be looking at is the change in input is from, look, I'm looking at from about whatever it is, 1.2 maybe. So let's say if I assume this is an amplitude of 1.2 at the start, here's my change in input. From 1.2 up to maybe about 4.8, giving me, what's that, 3.6. My change in output, we're looking at this range in amplitude. Which is maybe, again, we're going to guess this, maybe it's about 1.3, it's slightly higher than the other one. When you have your own data, you're going to be able to zoom in. But 1.3 up to about, again, we're probably better off to take an average here rather than the maximum or minimum value. So, what's that, about 5.4, 5.3 we'll say. So I'm looking at a change in output is equal to about 4. So my change in output we've calculated to be about 4. My change in input we've just calculated to be about 3.6, and I think we then have a ratio of those two, which is about 1.1. Okay, so change in output divided by my change in input. Now, for many of you, those of you that are working on the tanks, it doesn't matter about the change because you're starting at 0 in both cases. So the change in the absolute value is the same. If you're working off the thermal rigs, then those start at 20 degrees, or the starting point is like 2 So the change does matter then. Okay, because you then do need to factor that in. So my time constant, as I said, we're looking at 63% of the change. Well, so we're talking about the time taken for the response to change by 63%. So I'm going to calculate 63% of the change in output first of all. Which I think, if I've done that right, gives me about 2.5. Right, so for my time constant, I'm then starting here at my initial amplitude, I'm going up that 2.5, which is going to give me 3.8, about here, I guess. So it's the 2.5 on top of the 1.3. So looking the time it takes my output to change by 63%. So the initial amplitude is 1.3, the change is 2.5. So the total amplitude that I'm looking at is the sum of the two of those two things, 3.8. And then I'm looking at the time interval. So I'm coming down here. My response begins to change. Again, we're going to make an estimate here. This is going to be a bit of a curve, so we're going to take an estimate here. And my time constant is sitting in there. So in this case, what's that, about 0.7 of a second maybe, or something like that. So my transfer function sort of works out to be something like 1.1 over 0.7, 0.8, something like that, for my time constant, s plus 1.
If you never took it out, right? I never took off the 4 seconds at the start.
Oh, yeah. Give us.
So,
it's right for you.
So, in a first objective that we have in terms of, I guess, the practical pieces, you're going to gather your version of this data and obviously repeat this exercise. You're going looking at, the assumption is most of your data is first order. You know, it doesn't have any of those oscillations. Now, not all of your data has nice exponential curves, so it's not perfectly first order, but we're going to work with that assumption. We're going to assume that it's first order. At the minimum, you have a steady state gain and a time constant. And you're going to need to estimate those parameters from the data sets that you record. So that's, I guess that's the immediate plan. And then obviously we're going to check that those things are accurate and then move on from there. So, so that's going to be the plan. Next week is to start doing some of that, taking those measurements from your data and checking how accurate it is. Okay, so those of you that have data, that have it saved and have made sense of what we've talked about, we're finished. You just need to talk to you guys about making sure your data saved. Are you okay with saving the data?